In this video, we'll be going through a paper called Recursive Synthesis for Long Horizon Terminal Tasks out of Tencent and a group of universities. It's a paper about where practice comes from. If you want a model to get good at doing real work on a computer, it needs real work to practice on, and someone has to make that work. The paper's answer is to stop making it by hand. Start with the terminal. It's a plain text window into a computer. You type a command, the computer runs it, and it prints back what happened. That's the whole interface, and almost everything that keeps software running happens through it. Now hand the keyboard to a language model. That's what people mean by an agent. The model reads what's on the screen, decides what to do about it, and types the next command itself. Then it reads the new output and goes again. Model reads, model types, computer answers, around and around until the job is finished or the model gives up. The interesting question is how long that loop has to run. Fixing a typo in a config file might take 3 commands. A task on a typical benchmark takes around 40. The hardest tasks in this paper take 244. And they're not 244 independent commands. Each one lands on the machine the previous one left behind. Get command 12 wrong, and command 90 is quietly working on the wrong files. That's what long horizon means, and it's why these tasks are hard in a way that short ones aren't. So how do you train an agent on work like that? The basic recipe is give it the job, let it try, and reward it when it succeeds. Which sounds fine until you have to decide whether it actually succeeded. At 200 commands, no person is reading the transcript. Success has to be something a program can decide on its own. That takes 3 things. A workspace, meaning a real machine with real files and tools, starting in a known state. A goal the agent is actually told in plain language and told completely, because anything it will be graded on has to be stated up front. And a check that runs by itself afterwards looks at the machine and returns, pass or fail. Put those 3 together and you have what the paper calls a verified task, not a quiz question with an answer key. A working environment plus a machine checkable definition of done. And while the task is being built, there's a 4th piece too. Here's what one of these tasks actually looks like on disk. It's a folder with 5 parts. 3 of them the agent gets to see. The instruction, which describes the job in plain language. A small configuration file with runtime settings. And the environment. A recipe that builds the starting workspace fresh every time the task is run. 2 of them the agent never sees. There's a reference solution, a script that does the job correctly, which exists as proof that the task can be finished at all. And there's the verifier, the private test that decides pass or fail. One detail matters here. The verifier grades the state the workspace ends up in, not the exact commands used to get there, so the agent isn't being scored on copying a particular route. Any route that genuinely works counts. Look at those 4 working parts together and you can see why they're expensive. They all depend on each other. The instruction has to describe the job the reference solution performs. The solution has to run inside that specific environment. The verifier has to check the thing the solution produces and the instruction asks for, move any one of them, and the other 3 have to move with it. Keeping 4 moving parts consistent is human work, and the paper puts it at somewhere between $100 and $1,000 per task. That's the number that decides how much practice can exist. The obvious shortcut is to ask a model to write the whole task in one go. It's cheap, and it usually breaks exactly this consistency. The model writes an instruction describing one job, a solution doing a slightly different one, and a test checking something the instruction never mentioned, which is the real bottleneck. Not the model, the data. An agent gets better at long terminal work by practicing on long terminal work that can be graded, and every hour of that practice has to exist as a verified task before the training can use it. So you have 2 obvious options, and neither one works. Hire people to write the tasks, and capability turns into an authoring budget. Hundreds to thousands of dollars each, because a human is holding all 4 parts in their head. Or ask a model to invent them, which scales beautifully and produces tasks nobody can trust, with nothing proving the task is even solvable. RST is the attempt at a 3rd option. Generate them, but make every single one prove itself before it's allowed to count. Here's the whole idea in one loop. Don't invent a task from nothing. Start from a task that already works and is already verified. Make it harder, then prove the harder version still works. If it does, it becomes the seed for the next round, and you do it again. So, take a seed task. Synthesize a harder version of it by extending the solution and then bringing the verifier and the instruction back in line with it. That gives you a candidate which nobody trusts yet. Run the candidate in a fresh sandbox to see whether it holds up. If it holds, it's accepted, and it goes back around as next round seed. If it doesn't, it's thrown away. Everything accepted also feeds the training pool. The tasks themselves for reinforcement learning, the successful attempts at them as fine-tuning examples. Now let's walk through the 4 stages properly. First, decide what harder is going to mean for this particular task. The pipeline reads the seed, its files, its tools, its dependencies, what its solution already does, and picks one of 40 specific rewrite moves. They're grouped into 5 families: the environment the task runs in, the build and test workflow, the data and artifacts it handles, its configuration and state, and diagnostic work like reading logs and tracing failures. The choice isn't random and it isn't purely greedy. It weighs how well the move fits this specific seed, how balanced the 5 families currently are, and it penalizes moves that have already been used a lot in this batch. That's what stops one favorite trick from taking over the whole pool. Before anything gets edited, the model has to write down what it intends to do. This is a form it fills in, and it's the part that makes the whole thing work. It states the rewrite move it picked. One clear goal for the new task. What part of the old workflow survives? What the new requirement is. Then the chain of work in stages. What has to be inspected, what has to be worked out from that, what has to be built by actually running something, what has to be validated, and what the final deliverable is. Then the files that should exist at the end, and what has to be true about each one. 2 sections carry most of the weight. The reward checks, and there are always at least 4. There has to be real evidence in the workspace that the agent found and used. There has to be a real intermediate artifact, present and readable and not empty. The final result has to actually satisfy the goal. And there's an anti-shortcut check that rejects placeholders, empty files, stale output, and hard-coded answers written just to please the test. And then the instruction boundary, which splits what the agent gets told from what it has to figure out. The mention list. The goal. 1 or 2 fair starting points. The final deliverable, and any fixed value it couldn't possibly discover on its own. The hide list. Step-by-step commands. Complete inventories of paths and fields. Schema dumps. The actual repair recipe, and anything inside the test folder. Both halves exist for the same reason. An instruction that spells out every path and every field isn't a task anymore, it's a script to follow. Now the files get edited, and the order is the whole point. The solution goes first. It gets extended to inspect more, derive more, call more tools, manage more state, produce intermediate results, and check its own output. Then the environment is updated so all of that can actually run. Dependencies installed, fixtures and configuration added, services started, permissions adjusted. Then the verifier is realigned to check the new artifacts and the new state transitions, and to reject the shortcuts. And only then is the instruction rewritten to state the new objective and to name anything the agent genuinely couldn't discover. Executable behavior changes first, and the description follows it. That's the opposite of writing a prompt and hoping something implements it, and it's why the 4 parts stay consistent. You can see the effect on the reference solution. In round 1, the typical solution is 67 lines of shell. By round 15, it's 374. Then it gets tested in 2 phases. Cheap one first, because running a sandbox costs money. Phase 1 is a set of quick local checks. Throw the candidate out immediately if it's barely different from the seed it came from, if required files are missing, if its metadata is invalid, or if the private test has leaked into the public instruction. Whatever survives goes to phase 2, which is the real thing. Build the environment from scratch in a fresh container. Run the reference solution inside it. Then run the private verifier against whatever the solution left behind. If the verifier passes on everything, this task has been proven finishable. If it fails in a way that looks repairable, the failure logs go back to the model for a limited number of repair attempts on approved files only. Failures that persist are discarded. Nothing gets talked into the pool. An accepted task has the same 5-part layout as its seed and 1 extra file, recording where it came from, which round, which parent, which rewrite family, which specific move, and any repairs it needed along the way. That's the paper trail for the whole pool. Then it's time to pick next round seeds, and this is where caps come in. There's a limit on how many can come from one parent, from one category, from one rewrite family, and from one generation. Without those, a handful of prolific parents or one favorite rewrite pattern would quietly take over the later rounds, and the pool would collapse into variations on a theme. Two conditions decide whether a task is accepted, and both have to hold. The first is that the reference solution passes the private verifier in a fresh sandbox. That proves the task is actually doable. Somebody can finish it. The second is that everything the verifier checks is either stated in the public instruction or discoverable in the workspace. No hidden requirements. The agent is never graded on something it had no way of knowing. The first condition makes the task solvable. The second makes it fair. Together, they're what lets the process run on its own output without drifting into nonsense. Run that loop 15 times, and this is the shape of it. 639 verified starting tasks. Every accepted child becomes a parent. Failures get crossed out along the way. Past round 6, the branches stop fitting on the page, so they're drawn as a widening band. The color warms as the rounds go on, and that stands for difficulty. The same solver that finishes 90% of the round 1 tasks finishes 2.5% of the round 15 ones. What compounds is the pool. What stays fixed is the sample taken from it each round, and the caps applied to that sample. 639 tasks in, 37,484 out. Those are the headline numbers. 37,484 verified tasks with no human authoring anywhere in the loop. Round 1 alone turned the 639 seeds into 2,820 accepted tasks, and every round after that fed on the round before it. 327,000 recorded attempts at those tasks, command by command, in the sandbox. The successful ones become fine-tuning data, and 5 cents per accepted task, $50 per thousand against hundreds of dollars each by hand. The first thing to worry about when a process eats its own output is that it wears out. If reusing its own tasks were degrading the pipeline, throughput would fall off round by round. There are 2 ways to measure it. Out of every 1,000 seeds you attempt to rewrite, how many finished tasks come out the other end, and of the candidates the pipeline generates, what share clear the verifier. Neither one moves. Finished tasks per 1,000 attempts stays between roughly 498 and 572 every single round. 552 in round 1, 530 in round 15. The candidate pass rate stays between 74 and 82%. 78% in round 1, 78% in round 15. 15 rounds of feeding on itself, and the machine runs at the same rate on the last round as on the first. The tasks themselves keep growing. These are median values, round 1 against round 15. Control flow in the solution, all the branching and looping, goes up 7.5 times. File operations 7. Commands executed 6. Solution length 5.5. The number of distinct command line tools involved 4. Verifier assertions 3.5. And the instruction, the thing the agent actually reads, grows 1.4 times. 85 words to 122. That gap is the whole design. The work multiplies, what the agent is told barely changes, so the difficulty is going into the job rather than into a longer briefing. And the upper quantiles rise alongside the medians, which means the whole population is moving, not a few extreme tasks dragging an average. That's the pool in aggregate. Individual tasks do it too, and they keep doing it right to the end. Compare each child against the specific parent it was rewritten from. On average, the child's solution is about 30 lines longer, runs about 19 more commands, and gets about 4 more verifier assertions. And at round 15, 78% of parent-child pairs still grew rather than shrank on solution length. 77% on commands, 65% on assertions. Round 15 is still adding work, not just shuffling it. A harder task is worthless if it grades the agent on something the instruction never mentioned. So the tasks were audited on that directly, and later rounds turn out to be better specified than early ones. The share of tasks that don't leak their hidden checks into the public instruction rises from 38% to 64%. The share whose instruction isn't too short, to be fair, rises from 58 to 92. 2 other audits, no hints about the tests and no literal answers given away, were already at 100% and stay there. There's a stricter measure too. Of the requirements stated publicly, how many are actually backed by a check that runs? That rises from 42% to 57%. Tasks that were only weakly connected to their own tests drop from a third of the pool to almost none, and strongly grounded ones go from 14% to 38%. The tasks get harder and better, specified at the same time. Now the difficulty, measured properly. Take one strong model, hold it, and all its settings completely fixed. Give it 4 attempts at each task and change nothing but the tasks. On round 1 tasks, it fully solves 90%. By round 6, 20%. By round 15, 2.5%. A 36-fold drop. Because the model never changed, that decline isn't telling you anything about the model. It's measuring the tasks. The obvious follow-up. Is it failing narrowly or failing badly? Partial credit is the share of the verifier's checks an attempt satisfies, so it shows how close a failure came. It collapses along with the pass rate. Mean partial credit across all attempts falls from 97% to 17%. Among failed attempts specifically, from 78% to 16%. The median task goes from clearing every check to clearing 17% of them. The clearest version. Failures that still cleared 3/4 of the checks were 86% of all failures at the start and 1% at round 15. Tasks where the model scores below half the checks go from none at all to 97.5%. So these aren't almost solutions. Later failures are real failures, which means the difficulty is genuine and not just a stricter grader. And it isn't one model's weakness. 2 different frontier models, scored at 3 different bars for what counts as done, 70, 80, and 90% of the checks, from the seed pool through to round 15. Every line goes the same way. Neither model escapes at any threshold. One more thing worth noticing. The attempts that do succeed get much longer. Successful runs on round 15 tasks routinely pass 100 steps and often run between 130 and 170. The second thing to worry about when a process feeds on its own output is that it narrows. That it finds one kind of task it's good at generating and quietly produces that forever. 19 subject areas go in, from building and compiling software to system administration, security, containers, version control, databases, networking. 15 rounds later, the same spread comes out. The mix's evenness, measured as entropy, goes from 0.821 to 0.817. The effective number of domains, which is roughly how many areas are meaningfully represented, goes from 11.22 to 11.09, and no single domain ever holds more than 1/4 of a round. It doesn't narrow. Diversity is held on 3 axes at once, not just one, which rewrite families used. The 5 families stay near evenly split, with no family ever taking more than 29%. Which specific move? 36 of the 40 are still in use at round 15. The most common one accounts for 8% of tasks, and the moves outside the top 12 still make up nearly 1/3 of the pool. An ancestry. 218 of the original bootstrap seeds still have descendants at round 15, and the single most prolific seed accounts for less than 1% of any round. There's no dominant ancestor. Then the closest question of all. Is a child actually a different task from its parent or a reworded copy? Measured on the text itself, at round 15 the instruction differs from its parents by about 1/3, the solution by about 1/5, the tests by about 1/3. Real edits, not paraphrases. Within a single round, tasks do get more similar to their nearest neighbor over time, from about 22% overlap in round 1 to about 46% in round 15. But a typical round 15 task still shares less than half its text with the closest thing to it in the pool. Similarity rises. The pool doesn't become copies. And separately, all these tasks were checked against every task in the 3 benchmarks used to evaluate the trained models. No meaningful overlap at all, and the gap actually widens over the rounds. The training data isn't quietly containing the test. Here's what all of that looks like as one concrete task, followed from seed to round 15. The job never changes. Produce reliable comparison reports between JSON files. The seed is a handwritten example. Compare 2 pairs of fixed files in 3 output formats, 10 lines of solution. Round 1 moves the list of comparisons into a configuration file, so the agent has to read the config, run every comparison in it, and write a report. 66 lines. By round 5, the configuration can be broken, and the agent has to run a checker, interpret what it says, repair the config, rerun everything, and total up the changes. 219 lines. By round 10, a release note introduces a new test fixture, and the agent has to read the note, work out which comparison is now required, add it, and satisfy a local validator. By round 15, the configuration, the fixtures, the expected counts, and the tests all disagree with each other, and the agent has to reconcile all 4, regenerate everything, write both a diagnosis and a validation report, and pass the suite. 347 lines. 10 lines to 347 without ever leaving the task's original subject. Which leaves the question that matters. Does any of this make a better agent? First test, the simple one. Take the successful runs on these synthesized tasks and use them as ordinary training examples. Show the model good work and have it learn to imitate it. 2 model sizes, 3 benchmarks, and 4 points on each chart. The base model. Then checkpoints after 1, 2, and 3 rounds worth of synthesized data are folded in. Every line goes up at both sizes, and each extra round of synthesis still adds something rather than plateauing. The gains reach about 10 points, and they show up on Terminal Bench Hard, a benchmark built completely independently of this data, which is the version of the result that counts. Second test, the more demanding one. Use the tasks themselves for reinforcement learning. The agent attempts a task in a live sandbox. That task's own verifier scores the attempt, and the score is the reward. No human labels anywhere in the loop, which is only possible because every task came with a working grader attached. Both charts show training progress, 60 update steps, not synthesis rounds. On the left, the average reward, the share of a task's own checks an attempt satisfies. It's low throughout, because the pool is mostly tasks the model rarely finishes outright, and it climbs steadily from about 11% to over 14%. Slow, but never collapsing. On the right, how long the attempts run. 1 turn is a command plus the terminal's answer. Attempts go from around 19 or 20 turns to over 30. The agent stops walking away from hard tasks early. Both lines rising together is the claim. The tasks are gradable enough to give the training signal something to work with, and hard enough that the thing being learned is persistence rather than a trick. Here are the final numbers, averaged over 3 evaluation runs on each benchmark. The trained model is the 27 billion parameter one, after reinforcement learning on the synthetic tasks. It gains 20% relative on Terminal Bench 2, 41% on Terminal Bench Hard, and 22% on the Long Horizon benchmark, all measured against its own base. It also passes the much larger base model it started out behind. The biggest relative gain lands on Terminal Bench Hard, the benchmark constructed with no connection to this training pool at all. And the model that generated the tasks in the first place still leads all 3 columns. The trained model has closed part of the gap, not all of it. There's headroom left. Which brings us to the part the authors are careful to point out. After 15 rounds, nothing has run out. The yield holds. Finished tasks per 1,000 attempts has barely moved. Growth is still positive. Children still outgrow their parents at round 15. And diversity has survived. Domains, families, and specific rewrite moves are all still spread wide. All of that while the tasks got hard enough to take strong solvers from above 70% down to between 4 and 7. 15 rounds is where they stopped, not where it stops. So what does this buy you? A renewable supply of practice. 37,000 verified tasks at 5 cents each, with no author in the loop. The authoring budget stops being the ceiling on how much practice can exist. Difficulty on a dial. Later rounds are measurably harder within the same lineage, so the training pool can be aimed just past what the model can already do, and moved as the model improves, and it shows up in the model. 10 points from plain imitation, 41% relative on an independent benchmark after reinforcement learning on the tasks themselves. Which is the claim in one line, verified practice for terminal agents can be manufactured rather than written, the whole paper in 8 numbers. 37,484 verified tasks from 639 seeds, 5 cents each. Solutions 5.5 times longer by round 15. Instructions only 1.4 times longer. A strong solver falling from 90% to 2.5. Partial credit falling from 0.97 to 0.17. 10 points from fine-tuning alone. 41% relative gain from reinforcement learning on the hard independent benchmark. The paper is Recursive Synthesis for Long Horizon Terminal Tasks. The preprint is on Arschekbev, and the full set of 37,000 tasks is published on Hugging Face.